All right, so now with this one, we're going to go ahead and work backwards from what we had. So what we originally did on that first example is we were given a function, say 2n plus 5 equals a of n. Sorry, not a function, that is a sequence. So our sequence, we had our equation and then we found our terms. Now we're going to work backwards from our terms to our sequence formula, equation. So what we're going to look at is with A, we need to find this pattern between here and here. So -1 to -8, that means you are either multiplying by 8 or subtracting by 7. Then you go to 8 to 27, and that's 3. 27 to 64, so this looks kind of funky. This doesn't follow a perfect sequence pattern that we had on that last one. So we're going to go ahead, and we need to go ahead and try to find a different type of pattern. So let's now make the connection between what term we're looking at and the answer. So we would look at n for terms and a of n for our answers. That's like our x and our y. So our first term is a -1. Our second term is a -8. Our third term is a -27. And our fourth term is a -64. Can you look at this and see if there are any possible relationships between them? Well, 1 and 1's always hard to do because anything times 1 always ends up being 1. But we know there's going to be a negative, so we're doing something with a negative. Now, 2 to 8. How do I go from 2 to 8? Hopefully you're thinking to yourself, well, 2 squared, or 2 cubed is 8. Let's check. Is 3 cubed 27? Yes. And 4 cubed is is 64. But now we have these negatives we have to worry about. Any number that's cubed, if it's negative plugged in, you get a negative output. So what we can say is that we can see that this is -n cubed. If you need to go back through, you can check. So 1 times the negative, so -1 cubed is -1. You plug in a 2, -2 cubed is -8. So that works. So our function is a of n equals -n cubed. Hopefully you are able to pick up on that. Now looking at B, we've got 0, 2, 6, and 12. With this problem, you can't quite see, like you're adding by the same thing, you're multiplying by the same thing, and so on and so forth. But I can kind of see some form of pattern in the sense of things I'm multiplying. Now, the 0 is always hard to look at, but if I look at, I'll just write them out, 0, 2, 6, and 12. I'm going to look at something times 2 on this one because it's my second term. Well, 2 times what is 2? 1. 1 is actually the term prior to the second term. So I could go ahead and say, okay, this is my first term, and what's the number prior to that? Well, that's 0. So we're looking backwards at like a 0 term. Now, if I look at 6, that's my third term, and prior to my third term is my second term. And then 12 is my fourth term, and what's prior to my fourth term? My third term. So what I'm actually looking at is my term that I'm on times the term that was before it. Now, it's very abstract. We write this in a different type of sequence, which you guys will get to. It's called a recursive. If you guys remember from Math 2, recursive sequences are like the bane of every math teacher's existence because they are not very logically written out. Now, that's how you write the recursive. Another way you could write it is if you just multiply that n through. That would be n squared minus n. And you could also check that. So 2 squared is 4 minus 2, which you get 2. My third term is 6. So, sorry, my third term that I'm looking at, 3 squared minus 3. What does that get you? Well, 9 minus 3, that's 6. So we weren't able to find a pattern within our outputs, but only our inputs on this one. So that's more on the challenging side, and I am planning on addressing these in our next slide class. But if you need more, please reach out to me or look into that ebook where they've got extra tutorials.